In this class, we're going to start talking about logical equivalences. We've already noticed that sometimes statements can have identical truth values or sometimes maybe completely different ones. So in order to distinguish between the two cases, we're going to say that two statements P and Q are logically equivalent if and only if they have identical truth values for all possible truth values of their components. So notice here that P and Q, the capital letters, are used to denote compound statements. Normally, we reserve the little letters to denote something that's very simple, the component. So the little p can be true or false by itself, whereas the big P will probably be a combination of several of the smaller counterparts. So these two compound statements are logically equivalent if they have the exact same truth table values for all the possibilities. In that case, we write P logically equivalent to Q, which is instead of 2 bars is going to be 3 bars, or sometimes the notation is also P if and only if Q, but with the double arrows in the middle to indicate that this is not the same as the biconditional, but rather each half is a compound statement in itself that is equal in truth values for all of the components of the other. We've already constructed truth tables where we've noticed patterns, so let's flip back to page 3 and see which statements in there are logically equivalent. This is the truth table that we filled out back on page 3. So notice, as we have in that class, that some of the columns are identical to some of the others. So for example, we can see that these two columns, for every possible combination of the truth values, have the exact same truth values in themselves, which means that the two expressions corresponding to them are in fact logically equivalent, and we can write that down. So in this case, we have that the expression not P and not Q is logically equivalent to the expression not P or Q. The other things that this table has revealed is the fact that this column is equivalent or looks the same in the truth values to this column, which means that the two corresponding expressions here are also logically equivalent, and we can write that down. In order to keep maybe the same format, I'm going to write this expression first. So not P and, or not Q is logically equivalent to, so again, this column was the same as this column, not P and Q. And then finally, we also noticed when we filled it out that this column was identical to this column, which means that their corresponding expressions are logically equivalent. So P implies Q is logically equivalent to not P or Q. These are the first set of the proven logical equivalences that we have. So I just transferred over our observations here, but also notice the general strategy for deciding whether two statements are logically equivalent or not. The only way we can do that for now is, in fact, to construct a truth table, just like we did in order to find out that these expressions were equivalent. If they have identical truth values in every single row, then the two expressions are logically equivalent. Otherwise, they're not. If you want to write down the fact that two expressions are not logically equivalent, you would simply put a strike through the triple equality line here. So, since our only tool is constructing the truth tables, that's what we're going to be using for now. In this example, we're asked to prove or disprove the various logical equivalences of these statements. So we're going to construct the truth table for them and then see if the actual columns are identical. Notice that in all of these parts of this question, we only have P and Q. So we can actually construct the truth table for one truth table for all of these examples and then find out which ones are in fact equivalences and which ones are not. So we have true, 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 false, false, true, false, true, false. Now, the first one that we have to figure out is P equivalent to not, P. So if I am to construct every single column that I have to help me figure out this equivalence, I have the column for P. Now I'm looking for the column for the right-hand side. There's two negations, so I'm going to construct one at a time. So I'm going to have a column for not P, and then I'm going to have a column for not P. Now the column for not P will simply negate the column for P. So all of my values are going to be flipped. So I'm going to end up with false, false, true, true. And the not P column will simply negate all the values in the not P column. So I'll flip them right back. True, true, false, false. Now this isn't really unexpected. If I am to flip something to an opposite value and then back, I will end up with the original value. And I can see here that the column for P and the column for not P are identical in every single row, which means that this is a true logical equivalence. For the next one, I have P versus P and false. So I have a column for P. I do not yet have a column for P and false, so I'm going to construct that one. Let's see what this one gives us. P and false. So I have P, which in this row has the true value of true, and false will give me false. True and false is still false. False and false is false. And then finally, false and false is still false. So now I look at the two columns that correspond to these two statements, P and false. Are these columns identical? No, not at all. We have true, false, 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 false. They're not the same, which means that this is not a logical equivalence. So if we want, we can put a strike through that. Notice that there's a couple of other things that we could have done actually. First of all, it's P and false. So after filling in the first row and figuring out that they don't match, I didn't even have to fill out the rest of the column. I already know that it's impossible that they're the same value, so I could have striked it out as logical equivalence immediately. But it is interesting to notice that this entire column actually produced false as a value, which means that this expression is in fact what we called a contradiction a few slides back. In a similar fashion, we can check the other two expressions, P or Q and Q or P. So I will construct two columns, P or Q, and then I will follow with Q or P. And if they are the same, then we have the logical equivalence. I encourage you to actually go through and construct it, but yes, this will in fact be a logical equivalence. And the last one is the most complicated one. So I have not P, whose column I already have created here. But then I also have P or Q, which I will have here, and then followed by P and P or Q. Once I fill that out, I will be able to tell if this column is identical to the not P column, then they will be logically equivalent, and otherwise they will not. The reason that I know that this one is certainly a logical equivalence is because this is one of the commonly used logical equivalences throughout. So notice that this is a pretty onerous process. Every time I have to figure out a logical equivalence of something, I have to construct a truth table for it. But once I do go through that process, once I have proven that two expressions are logically equivalent, I can use that fact from then on by itself. Never again will I have to construct a truth table for it. I can simply use that as a rule or as a law. And this is where this useful logical equivalences tables comes into play. I want to emphasize the fact that these logical equivalences rules are not given to us by some higher power. They are the rules that we can prove and have been proven using truth tables. It's just, once again, once they're proven, we don't have to draw truth tables. We can just use them as a shorthand. However, if you're ever asked to show that one of these laws is actually correct, in order to prove logical equivalence, you will have to go through the truth table. Now let's see what kinds of laws are actually useful as shorthands. First come what are called commutativity laws. So the order of the or and the and operation doesn't matter. P or Q is the same as Q or P. And this is kind of reminiscent of the fact that 2 plus 3 is the same as 3 plus 2. Associativity laws is something that I've hinted at before. If you have the same operation throughout, where you place the brackets doesn't quite matter. And again, this is similar to what we see in arithmetic. If I have pluses throughout, then it doesn't matter if I add 2 plus 3 first or if I decide to add 3 plus 5 first. Distributivity's laws deal with the case when the operations are different. So if we were to compare this to the arithmetic, this would be something like if I have P times Q plus R, then in order for me to open the brackets, I will distribute everything in. So I'll have P times Q plus P times R. And this is in fact exactly how the distributivity laws work in logic as well. Interestingly enough, right? Clearly, this is not the same at all, but it has the same feel, and we can prove these using the truth table, not some kind of arithmetic. But the analogy is fairly useful. So notice that whatever operation I have on the outside here is the operation that gets distributed to both pieces. So I started with the and here, and it got distributed to 2 of the internal pieces. But the operation that was in the middle stayed as the one connective. So the operation connecting Q and R here ended up connecting the 2 parts here. The identity laws and the negation laws somehow look similar to what we've already discussed in terms of tautologies and contradictions. The double negation law is the one that we have just proven using the truth table. If you negate something and then you negate it again, you will be back to the original thing. Idempotent laws tell you that if you have P and P, or P or P, you will end up with just P. The truth value of both of them is the exact same as the truth value of the P itself. The universal bound law is also kind of similar to identity laws. Take a look at those for a minute and try to persuade yourself that that is in the case true. De Morgan's laws is what we actually saw from the page 3 table and are, in fact, both very interesting and very useful laws. They allow you to distribute the negation into an operation. So let's see how this works. When you distribute the negate in, it essentially affects both the statements and the operation in the inside of the brackets, and everything gets somehow flipped. So if you have not P and Q, you will apply not to P. So you have not P. Then you apply not to and, which actually turns it into an or. And then you apply not to Q, which turns it into not Q. Okay? So if the negation is applied to a conjunction, you get yourself a disjunction. If the negation is applied to disjunction, you get yourself a conjunction. Okay? So this is, in a way, how those two operations are sort of opposites of each other while not actually being the negation of each other. Absorption laws allow you to make more complicated expression smaller, and this will come in handy in some simplifications. And the implication law is again the law that we actually saw proven on page 3, and this law allows you to turn an implication into a disjunction. Notice that the implication law is the only one that has the conditional in it. Everything else in this table deals with or and that's exactly why that can be the case. We can in fact turn the conditional into an or and then apply whatever laws are actually useful for the disjunction on top of it. Once you get rid of the implication, everything else in this table will become immediately much more useful. So again, once you have these logical equivalence laws, you can use them directly without having to go through the truth table. So let's see how this helps us simplify things as expressions without constructing large truth tables and without having to go through the columns and maybe compare them to each other. So we are going to try to simplify these two separate expressions. Let's start with this one. So what do we have? We have P or, not P and Q. Looking at the table, we have to figure out if there's anything we can use immediately. Notice that the operations here are different, so the only thing I can apply right away is distributivity law. This one is an or followed by an and, so the distributivity law I'm going to be following is the second one here. Distributivity laws are probably one of the hardest ones to spot, especially because they can be used in either direction, as we will see later on. So I encourage you to try, now that you know that you have to apply this law, try to apply it to this statement before I do. So pause the video and try to see if you can carry this law through this expression here. So what we're going to have is I'm going to write this is equivalent to, because I'm applying one of the laws, and then follow through with the distributivity law. So I'm going to have P or the first thing on the inside bracket, which is not P, and P or Q. Okay, again, the outside operation got carried into both brackets, and the internal operation stayed as the middle. Okay. Whenever you do simplifications with these things, we write down what law we actually applied. This keeps track of the operations, and it also serves as the proof that every step you have actually applied is justified through something that we know to be a logical equivalence. What can we do at this point here? P or Q seems like a fairly tight unit, but P or not P surely can be simplified. So if we scan the table for that expression, we will actually spot it exactly here. Negation law. P or not P is always true. So my next line will be replacing this by true, and then I have P or Q as something that I have not changed. And again, I'm going to label this as negation law. So this justifies why I was able to continue writing equivalence, because this law gives me a known equivalence. Okay, well, what can I do at this point? I have true and something. Is there anything in the table that will help me along with that? Well, here is where you have to start sort of learning how to squint. It's the structure that's important, not necessarily the exact right components. So I have true and something. Is there anything in the table that's useful for that structure? I can see that in the identity law here, I have true and something is equivalent to that something. So I can apply the equivalence law here to this expression. True and something is simply that something. So this is equivalent to just P or Q by the identity law. The main idea is you always have to think in terms of a structure. So for example, commutativity laws don't have to apply to just little expressions P and Q. Any expression or any other expression is equivalent to the exact same thing but in the opposite order. As long as your connective is or, these two will be equivalent. So it doesn't have to be just P and it doesn't have to be just the Q. It can be any larger or more compound expressions within. Now P or Q is the basic operation, so there's nothing else we can do to simplify that. That's as far as we're going to be able to go. Let's take a look at this. So here we have not P implies Q. Notice, once again, brackets are important, that the brackets are first of all on the second expression here. As I already mentioned, vast majority of this table deals with ands and ors, and only one line gives us a way to go from the implication to the disjunction. So this is the one we have to start with. In order for us to be able to simplify anything in any possible way, we have to actually get rid of the conditional first. So I'm going to apply the implication law to this internal bracket first. So I'm going to have not P implies, but now my P implies Q will be replaced by not P or Q. And again, I'm going to indicate what law I applied, implication law. Okay, what's going to be my next step? Well, I can't open up these brackets yet because I don't know how to open up the brackets with the conditional in front. So my only other choice at this point is to get rid of this conditional. And again, that's when you're going to have to be quite careful about how you apply the laws, because you have to remember that they apply to components, not necessarily just the variables. The implication law says thing 1 implies thing 2 is the same as not thing 1 or thing 2. So this implication, this is my thing 1, and this is my thing 2. So I have to negate the first portion. So it's going to be not P. And then the implication law says or, and the second portion stays as is, not P or Q. Okay, let me write this down and we'll go over that again. So I have not P or not P or Q. And this once again is the implication law. Okay, let's see why this works again. You have thing 1 followed by thing 2. By the implication law, I have to negate the first portion. So there it went. That's my piece. The implication gets replaced with an or, and the second part stays intact. This is what the structure actually implies. 1 implies Q is the same, implies 2 is the same as not 1 or 2. Okay, let that sink in a little bit. Make sure, again, you sort of squint and see the structure, not exactly the P and the Q, and then hopefully this actually makes sense. Once we're here, what can we do at this point? Well, I can see the not P, and so I can certainly apply the double negation law to get rid of that. So I'm going to have not P replaced by just not P, or not P or Q. And this is going to be the double negation law. Once I'm down to this point, I can notice that the operation throughout is the same, so I could regroup my pieces if it was convenient. And just like in this case here, I know that if I have just a simple disjunction between the P and the Q, it's probably not simplifiable, but if I can group the P's together, I should be able to either apply some sort of absorption law or apply one of the idempotent or negation laws or something along those lines. So let me apply, first of all, the law that's called associativity, my ability to move brackets throughout if the operation is the same, and then see what I get from there. So in my next step, I'm going to have the brackets are going to be moved to the front. And this is possible because of the associativity law. Associativity law. Now that I have this and the P's are grouped together, what do I have? I have P and not P. Where in the table can I see something similar like that? P or not P? Well, P or not P is actually right here. It's the negation law. And that is always going to be true. So I can replace this with true or Q. And the law that I used was the negation law. And now that I have this expression here, true or Q, is there something that will help me here? True or something? Well, there's this, true or something. Again, it doesn't matter whether it's P or Q or P implies Q or anything like that. The structure is true or something is always true. So true or something is always just true. Remember that or is always true as long as one of the components is true. Is this one is guaranteeing true, the whole thing is going to be true. And I can say here that this is by the universal bound law. This is actually quite powerful because notice that I took an expression that was quite complicated and I showed that it's actually logically equivalent to true, no matter what the values for P and Q are. That is the same as if I constructed a truth table for the whole thing and then found out that every single entry in the final column is true. This just proved that this expression is in fact a tautology, without having to go through the pains of constructing a fully blown truth table. Following through the laws is a different approach, but is usually much cleaner. It's much easier to make a mistake in a giant truth table full of the T's and the F's or the zeros and the ones than it is by following through one step at a time by applying laws. The key here is to, again, make sure that you look for structure and not just for the exact same expression as the one in the table, and also write down all the laws you're applying to justify that you're able to go from one step to the next. Another way to use the logical equivalences is not just to simplify expressions, but rather to prove that they are equivalent. And this is probably going to be the more important way to apply them. So here we're asked to prove that the left-hand side is equivalent to the right-hand side. Without the logical equivalence tables and the laws, the only way to do this is to construct a truth table and to show that the column for this expression is the same as the column for this one. But logical equivalences give us a bit of a shorthand in that. Now, there's a couple of ways one can approach this. You can start with the left-hand side and try to simplify, hoping that it will look like the right-hand side, or you can simplify the left-hand side and get to the expression that you like, and then simplify the right-hand side and get to the expression that you like, and then hopefully it will be clear that they are the same. Okay, let's see what we can do here in terms of first simplifying the left-hand side. So I'm going to start with left-hand side, which is not P implies Q. Now, as we've already discussed, the only way to get rid of the implication is to apply the implication law. So the first thing I'm going to do here is get rid of the if-then by replacing it with not P or Q. So the application here was for the implication law. The next step is to somehow open up these brackets. So remember that in order to open up the negation into the bracket, the one tool I have going for me are the De Morgan's laws. This is also probably when it becomes really clear that it's nice to have that table of logical equivalences handy so that you can constantly refer to it. It might be easier if you print it and keep it by the side of your desk when you're working through the homework, as opposed to having to look it up every single time. The De Morgan's laws say that I can put the negation right in and negate both of the components as well as the operation connecting them. So here I'm going to have not P, because I am negating the not P. The or will turn into the and the negation applied to Q will produce the not Q. So this is by De Morgan's laws. Next, as we've already seen, and remember, I can, of course, get rid of the not P. Not P is simply just P, so I'm going to end up with P and not Q due to the double negation law. Well, it doesn't seem like I can simplify much further, but I'm in luck because this is in fact my right-hand side. So I've just proven that my left-hand side is equivalent to my right-hand side, and I am done. We have verified the validity of these two expressions. Now, I am going to emphasize this one more time. When you are writing these down, you have to include laws that you are applying because these are proof that every single step was justifiable, that you could actually write down that it equals to the next thing that you were putting there, okay? So since my left-hand side is here equal to the right-hand side, we are done. Let's take a look at this one here. So what do I have? I have to prove the equivalence. On the left-hand side, I have an implication, and on the right-hand side, I have a negation of a conjunction. So I'm going to start with the left-hand side here. So let me rewrite this. P implies not Q. And again, the only way to deal with the implication is to turn it into a disjunction. So once again, remember that the implication law says thing 1 implies thing 2 is equivalent to not thing 1 or thing 2. So what I'm going to have in this case is not P or not Q. And this is by the implication law. Now at this point, our expression doesn't really contain brackets or double negatives or known truth values, so there seems to be nothing we can do here to simplify it any further, which means that it probably might be a good idea to take a look at the right-hand side and simplify that. So what do we have here is we're going to start with not P and Q. And again, using De Morgan's laws will allow us to bring the negation in. So I am going to negate the P and turns into or, and then we're going to negate the Q. So this was the application of the De Morgan's law. And now, of course, at this point, we notice that our simplified versions of the left and the right-hand sides are identical, which means that we have just proven the actual equivalence of the two. The sides being identical means that they are logically equivalent. Remember that when we started talking about the truth tables, one of the applications was to the combinatorial circuits. And the way to prove that two different combinatorial circuits were equivalent was to construct a truth table for each one and compare their values. Now that we have logical equivalence laws, we don't need to go through the truth table way. We can simply construct Boolean expressions for each one and then use the logical equivalences to show that they're the same. So first of all, we have this giant circuit here, and we will have to come up with an expression to describe it. So let's follow through where the operations are occurring. P went into the AND here and the AND there, so we will mark it as the entrance point on each one of these. Then Q went through the NOT, so I have NOT Q here, which means that on the output of P and not Q, I have P and not Q. What do I have for the second input into this AND is, of course, my Q. And so the exit here will be P and Q. Finally, on the input here of the OR, I have these two expressions. So this is what's going to be my output here. It's going to be P and not Q, or P and Q. And the last gate is this gate AND that has this as one of the inputs and simply Q as the other input. So overall, my final expression, which we're going to call R here so I can actually refer to it at the beginning, is P and not Q, or P and Q and Q. Okay, give it a second here. Stare at this carefully to make sure that you actually agree that this is the final output expression for this Boolean circuit. The expression for this Boolean circuit is obviously a lot easier because I just have two inputs into the AND gate. So my overall expression here is going to be P and Q. And the question is, are these two circuits equivalent? Can I prove that this expression is equivalent to this one? Well, let's see what I can do in terms of applying equivalence laws. First of all, let's look at the overall structure of this expression. It's pretty complicated. My last thing here is AND Q. So considering that this can't be simplified, maybe let's look inside here first. And I have two different operations here. Remember that I told you that distributivity laws are probably one of the hardest ones to apply because you can do them in both directions. So let's take a look at this table here again. Oftentimes, we think of distributivity laws as taking something with fewer brackets and turning it into something with more brackets. But you can also go backwards. If you start with a bigger expression, you can shrink it down to the smaller one. And that's exactly what we're going to do here. The expression we're working with now is of this form. Okay, maybe write this down so you can actually take a look at it. It has an or in the middle and two ands in the internal brackets, which means that if we can find the common variable, we can factor it out in this distributive law fashion. So what that translates to here is, look how we have this p in both of these brackets. We can essentially take it out. So what we're going to end up with is p, and then you just have to be careful about which distributive law you're using. So I'm going to write down the expression, but make sure you double check it with the table so you know how I actually got the expression I just got. So I'm going to have p, and what's going to be left in the brackets is the second halves connected with the internal operation. So not q or q. Not q or q. And then I have this and q on the outskirts that I haven't dealt with yet. This was the distributive law. Now, the thing to spot here too is now I've ended up with an expression that involves q and not q, and that is certainly something that's going to be in the truth table. In fact, we know that this is one of the laws. Which one it is? Let's take a look. Something and, or not itself is going to be of this structure here. The or will always produce a tautology if you're oring together the thing and not itself. So this is what the negation law will give us as the result. So here we can say that this is equivalent to p and true and the q that remains on the outside. So this is going to be the negation law. Now that we are into the next step, what do we have? We have p and the truth. And if we take a look at the table, again, I'm not going to flip back. As I said, it's probably better if you have it printed and next to you at all times so you can refer to it easily. You don't have to memorize the laws. You can always keep the table next to you during the exams as well as during your homework. So looking stuff up is a more important skill than memorizing it. Here we have p and true, which will be simply p, and then my and q gets transferred here. This is according to identity law. And we are done, because this is exactly the expression for the second Boolean circuit. So just like that, we have proven that they are in fact equivalent. This is a very powerful tool, because notice that this allows us to say that instead of actually constructing something like this in the hardware of a particular device, we can simply construct this much smaller gated Boolean circuit. And instead of constructing a big truth table with lots of columns and therefore lots of rooms for mistakes, we were able to prove the equivalence in just 4 short lines. Another one of the applications to networks is actually a switching network. So not a gated network, but rather a switching one. The concept is very similar. We have switches that can be turned on and off, and they're connected in a series or in parallel. So when we have a connection in series, we, similarly to the open and closed gate, have the expression that corresponds to this being and, because if both of the switches are on, the current will go through, but as long as one of them is off, the current will get stuck. And we can have the switches being connected in parallel. So that means that as long as one of them is true or connected, the current will be able to make it through. So this corresponds to the expression of or. And then the problem is similar to the combinatorial circuit one. If I start with the switching network, can I somehow make it smaller? Can I maybe simplify it in a way that will allow me to show the equivalence to a much smaller and maybe simpler network? So here we have a switching network that we are asked to make simpler. Note that B prime here actually corresponds to not B. So what do we have all together in terms of the expression for this network? That's what we're going to have to figure out first. So as before, we're going to follow inputs and outputs. So the wire gets split here, which immediately indicates an OR to both of these because the parallel construction corresponds to an OR. Then we have A and not B back to back. So that means that overall on the exit here, I'm going to have A and not B. The situation is a little bit more complicated on the bottom because I have another split here, which corresponds to an OR. A and B here are followed back to back in a series. So on the output here, I have A and B. But then I connect back through the parallel construction together with C. So what I'm going to have on the output here is going to be A and B or C. Okay, and again, now I'm going to have two of them come together through the parallel construction. So the overall output will correspond to my two latest currents being put together in parallel using an OR. So I have A and not B from the top, or A and B or C from the bottom. And that is the expression that I'm working with. We're going to try to simplify this to see if we can produce a smaller circuit. So what are we going to be able to do first? Notice that these square brackets that I've put up last don't actually have to be there because the operation that they are separating is this OR from this OR, and I can regroup them. This C is not much of a help in terms of simplification, and maybe having these A and B and A and not B expressions together will be more helpful. So the first thing I'm going to do is just that. I'm going to regroup inside the square brackets. Okay, and leave my OR C there. The law that allows me to do that is called associativity law. The ability to move brackets around as long as the operation is the same. And now I'm actually kind of in a similar situation as I was here. On the inside, I have two things that have something in common that I can factor out. And in fact, the rest of the simplifications will look very similar to my previous network. There was a different network, but apparently follows kind of similar rules as this one. So I can use distributivity law to factor out my A and end up with not B or B or C on the outside. So this was the distributivity law applied sort of in the less familiar opposite direction. And then I can follow the exact same things I have here. So I'm going to do a bit of a shorthand and say that B or not B is always going to be true as per negation law, which means that then I'm looking at A and true, which will be equivalent to A. And so what I'm going to have left is going to be equivalence to A. You know what? Let me write this here. A, and then of course this or C that we haven't touched. Since A and C are actual switches, there's nothing else I can do in order to simplify that. So this is going to be as simple as this network is going to get. If I am to draw A or C, I have to think of the parallel construction, and then I can say that this network is equivalent to the network where I have switches A and C connected in parallel. Notice again how powerful this is as a tool. I have a complicated switching network that I can show is equivalent to a much simpler one And therefore, if I am to implement this somehow in hardware, I don't have to put in quite as many switches and quite as many wires in order to create something that is logically equivalent and therefore will follow the exact same current rules as the other one. I've also managed to completely get rid of the switches B and not B, which again will save me quite a bit of work in the hardware. It's also interesting to think about how the switching networks actually correspond to the gated networks throughout, but we will work with them together in various applications of the logic in this course.